We're all familiar with the concept of mass. Objects that have a lot of mass, objects that have a lot of mass are a lot harder to move around than objects that don't have as much mass. And this is because objects that have mass have a property called inertia. Let's write that out. Inertia. Which can be thought of as the resistance to accelerate. So therefore, objects that have more mass and consequently more inertia are harder to get accelerating than objects that don't have as much inertia. Now, the same holds true for rotational bodies. If you've ever been on something like, let's say, a roundabout in a playground. Let's just draw one out. Little fences so the kids don't fall off. So let's say you're on a little roundabout in the playground. If you've ever tried to push kids on it, you'll realize that it's actually kind of difficult to get it to rotate. You actually need some effort as well. And just like objects that you're trying to accelerate in a linear fashion have mass or inertia, rotating objects have rotational mass or moment of inertia, it's called, which is just the rotational inertia. Moment of inertia. And we find that the more massive the merry-go-round or roundabout is, the more moment of inertia it has, or also the wider it is, or the bigger the radius, the more moment of inertia it'll have. Which is why when skaters pull in their arms, they spin faster, because they decrease their moment of inertia. So we know that the moment of inertia, let's call it I, the moment of inertia can be written in terms of the mass and the radius. Now we won't find the moment of inertia equation for a disk or any other shape because it's pretty difficult. So in this video we'll focus on the moment of inertia of a single point. So say if you have one ball or one kid here and you want to see how difficult is it to get this kid to rotate along with the roundabout. Let's say the kid has a mass m and is a radius r from the center of the roundabout. So we want to find out what the equation would be for the moment of inertia of this kid. So let's just recite some equations we know, so maybe we can derive the equation. We know that the torque, might as well write out some rotational equations, is force times lever arm length or radius. We also know that force equals mass times acceleration. Now for force equals mass times acceleration, there's actually a rotational counterpart. So what's a rotational force? A rotational force, well, is just a torque. Rotational mass, well, we already talked about this. Mass is inertia, right? So rotational inertia is a moment of inertia. Let's call it I. And a rotational acceleration is just, let's call it alpha, rotational acceleration. Now we want to find out what I is in terms of m and r. So let's just start combining some equations. Let's combine these two. So I times alpha equals torque, which is also force times radius. And if we isolate I, that's force times radius over angular acceleration. And remember, force can be broken down into mass times acceleration. So mass times acceleration times the radius over angular acceleration. Now be really careful. These two accelerations do not cancel because this is linear. So this is linear acceleration, linear, while this is rotational or angular, rotational. So what we could do to kind of simplify that equation and start canceling out those two accelerations is we could relate the two. Now how could we relate the two? Let's say you had a circle and an object started on one side, let's say over here, right? So it started on this side and it moved to over here. It would have moved a certain angle around the circle. Now depending on what the radius is, this distance is actually equal to the angle times the radius, because the angle is in radians, which is just radius lengths. So if you have radius lengths times the size of the radius, it'll give you the total distance. For example, if this angle is, I don't know, 1 radian, and the radius is 2 meters, you will go 2 meters, this arc length will be 2 meters. So we have that distance equals the angle times the radius. Oh, and also another way to prove this is, if you want to find the distance the entire way around the circle, what would your angle be? Well, there are 2 pi radians in one entire circle, and then times the radius, that's 2 pi r. Well, that's the circumference of the circle. So that just kind of proves the equation works. Anyways, let's go back to the distance is the angle times the radius. What can we do to get these to acceleration? Well, if you divide by a change in time on both sides, a distance divided by a change in time is a velocity. And an angle divided by a change in time is an angular velocity, which we can write as omega. Omega is just angular velocity in radians per second. Now if we divide by change in time again, what's a velocity times divided by the change in time? Remember, it's acceleration. And an angular velocity divided by a change in time is just an angular acceleration. So, if we divide both sides by angular acceleration, we get linear acceleration divided by angular acceleration is equal to the radius of the circle. So if you go back to our original equation over here, let's just write it out again. Moment of inertia of a point is m r a over a. Over alpha. This linear acceleration over angular acceleration we determined is actually just r. So we can rewrite this as I equals m times r squared. And that's the equation for the moment of inertia of a single point. So, let's say you had, just as an example, if on your original roundabout the kid was 30 kilograms and was 2 meters away from the center, their moment of inertia would be I equals mr squared. M would be 30, so 30 kilograms times 2 meters squared, which would be 30 times 4 is 120. 120 kilograms meters per second. Sorry, just meters squared. Kilograms meters squared would be your moment of inertia of the kid. And you can use this using the torque formulas to find out how fast something accelerates, if you give it a certain torque, and stuff like that. So, I hope you learned something.